Welcome to module 1 of lecture 7. In the last module, we took a look at when are two operations said to be compatible. We also understood two important resource sharing models, the compatibility graph model and the conflict graph model, and we saw that a solution to the compatibility graph model in terms of finding the minimum number of clicks in it. A minimum click partition of the compatibility graph gives me the maximum resource sharing possible. We also saw that a minimum coloring of the conflict graph gives me an optimal solution to the resource sharing problem, but we told that both the minimum click partitioning problem and the minimum graph coloring problem is NP complete for general graphs. Then we understood that there are a few special classes of graphs, that are chordal graphs, interval graphs, and comparability graphs, for which these problems have polynomial time optimal solutions. We understood that the compatibility graph corresponding to the operations within a simple data flow graph within a basic block can be modeled as an interval graph. Why? Because each operation in an operation within a single operation constraints graph within a basic block can be modeled as single continuous intervals from the start of its execution to the end of its execution, and hence the corresponding conflict and compatibility graph with respect to this scheduled operation constraint graph can be modeled as interval graphs. As we said, next, after understanding the resource sharing models, we will study algorithms for resource allocation. We said that interval graphs gives us easy algorithms for graph coloring in polynomial time, and these are optimal solutions. We will study one of these algorithms in this lecture, but before that we will understand the resource minimization problem. We will understand the resource minimization problem can also be mapped as a graph coloring over interval graphs, and hence the same graph coloring algorithm can be used both for functional unit minimization, that means maximization of resource sharing among functional units, and maximization of resource sharing among registers as well. And hence, before going to the actual coloring for interval graphs, going to the actual algorithm for coloring interval graphs, we will first understand the register minimization problem. The problem is to minimize the number of temporary registers used. So, we see that there are 4 independent variables here, x, y, z, w, and hence 4 registers will anyhow, 4 hardware registers will anyhow be required to store these variables. So, for these operations to be scheduled in time step 1, before time step 1 is activated, x, y, z, w must be in different hardware registers for these operations to execute correctly. Now, that is out of our control. However, these temporary registers, we said that the output of the operations are floated on temporary registers. So, each operation is floated on a different temporary registers at the output of the scheduling step. Now, the register minimization problem is to minimize the number of hardware registers that are required to allocate these temporary registers. So, these temporary registers must be allocated to hardware registers as well, right, when I actually implement the schedule, and hence I want to reuse a given hardware registers for as many temporary registers as is possible. This is how I do register minimization. So, what are the properties of temporary registers? At any C step, a temporary register may appear only once on the LHS when it is written and multiple times on the RHS when it is read. For example, this temporary register T1 is written in time step 1 because it is at the output of operation 1. Subsequently, this temporary register has been read in time step 2. So, it is read by this multiplication operation here and this addition operation here. This T1 is read in both these operations and both these operations are in time step 2. Right. If we take another example, let us take T2. So, T2 is written to in time step 1 and is read in time step 2 by this multiplication operator and is read in time step 3 by this multiplication operator. So, a temporary register will occur at most once on the left hand side of a register transfer and will appear and may appear multiple times on the RHS of a register transfer. And each register therefore has a distinct lifetime interval from its first definition to its last use, and hence these temporary registers can be mapped to distinct intervals. So, what do we infer from all these intervals? We infer that registers with non-overlapping lifetimes can be merged. So, temporary registers whose lifetimes are non-overlapping can be merged and allocated the same instance of a hardware register. For example, here T1 and T4 can be allocated to the same instance of a register. And so, what do the algorithm basically look like here? We sort the intervals based on their left edges, and then we take one hardware register which is blank and we take the first temporary register and put that in that hardware register. Now, say R1, I have hardware register R1 and I have put temporary register T1 into R1 because this has the earliest left edge. Now, I can put another register which is the earliest temporary register, means which is the earliest starting temporary register that I can put again in R1, any register whose left edge is higher than this right edge of T1, right. So, therefore, T4 is one such, T4 is the next such earliest starting temporary register which can be allocated to R1. Similarly, I can also allocate T6 to R1 because T4 and T6 are non-overlapping, the intervals are non-overlapping. So, I can put into R1 T1, T4 and T6. I can even put T7 into R1. So, therefore, the same register R1 can be used to hold T1, T4, T6 and T7. Likewise, then all these when I have already allocated a set of temporary registers to a given hardware registers, I now remove all these registers from consideration. From the remaining, so no remaining temporary register can be allocated to the hardware register R1. So, I put aside R1 with its allocation T1, T4, T6 and T7. Now, for the remaining register, for the remaining temporary registers, we try to allocate again the minimum number of hardware registers that I need to allocate these temporary registers in a very similar manner. So, the algorithm that we have can be formulated as a graph coloring problem. So, this particular register conflict graph. So, this is a register conflict graph. For the register conflict graph, this register conflict graph is also called a register interference graph. Now, the register interference graph has nodes as the initial temporary registers. The edges denote overlapping lifetimes, right. For simple DFGs, register interference graph is an interval graph, right, similar to the fact that for simple DFGs the functional the behavioral operations in my operation constraints graph are also have a simple continuous intervals, and hence their conflict graph can also be represented as an interval graph. Here again the interval graph or the conflict graph for registers can also be similarly mapped as an interval graph. Now, as we said, the generic problem is NP complete. However, for interval graphs the optimal problem can be solved in polynomial time. The optimal graph coloring can be solved in polynomial time, and in fact in n log n time, and that also in n log n time, because prior to the algorithm I need to sort the left edges of all the temporary registers in a list. So, what are the left edges? Left edges are the start times, the definition times, the first definition times of the temporary registers. So, I need to keep a list which maintains all my temporary registers that have not yet been allocated into a list, sorted in terms of their start times or their definition times or their left edges. So, in the interval graph I have a set of intervals Lj Rj. So, this is the Lj to Rj is the lifetime for temporary register Tj. Now, we need to assign a distinct color to a temporary register. What does this assignment of color means? A distinct color, if I assign to a temporary register, mean that I have assigned a distinct hardware register to this temporary register. So, this list I of all temporary registers are taken as input by the left edge algorithm. Now, given this list of intervals, it first sorts this elements in I in a list L in ascending order of the left edges. First, I assign 0 colors, means C equals to 0. What does C mean? C gives a labeling for colors. C equals to 1 is a distinct color, C equals to 2 is another distinct color, C equals to 3 is another distinct color. So, if I allocate a color C equals to 1 to a set of temporary registers, then all those temporary registers will be allocated to the same hardware register whose color is labeled 1, right. So, while there are intervals still left to be colored, we will take a hardware register, we will take a distinct color and find out what are the maximum possible number of temporary registers that can be allocated to this hardware register. What is the maximum number of temporary registers that can be assigned the same color? Okay. So, how do I do that? First, S equals to phi. That means, S will contain, S is a hardware register I have initialized, and currently it does not contain any temporary register in it, and hence S equals to phi. S is the set of temporary registers that can be allocated to a single hardware registers in each given pass, with this while loop is a pass. Firstly, R equals to 0, the initial coordinate of the rightmost edge in S in the hardware register is set to 0, while there exists an element in L whose left edge is larger than R. That means that I want to find a left edge in the list L, and in the list L all my left edges are sorted in increasing order. The first left edge beyond the value R in the hardware register defined by S currently is the register which I can allocate next to S. So, small s is the first element in list L with Ls greater than R. Then S equals to S union small s. That means, I include this register small s in the current set, in the current hardware register being considered for allocation, that is capital S. Then I change R equals to Rs. So, now I change the rightmost edge in my hardware register R to the right edge of the current temporary register that I have just allocated to S, because the next temporary register that can be allocated to S will have a left edge which is greater than Rs. Otherwise, their intervals will be overlapping and I will not be able to allocate in the same hardware register. Now, because S has small s has already been allocated a hardware register capital S, I delete S from capital L, which is the list of temporary registers which have not yet been allocated. And then I assign the color, I assign C equals to C plus 1 a labeling of color to capital S, that is a hardware register. Okay. So, label all elements of S with color C, right. So, then all these temporary registers are allocated to the same hardware register having color C. This loop will then continue until all temporary registers have been allocated hardware registers. So, like we have applied this problem for register minimization, I can likewise apply this problem for functional unit minimization as well. In that case, for each type of operations that are schedulable by the same type of functional unit, I will have to run this algorithm once to obtain the minimum number of functional unit instances that are required to allocate the behavioral operations of that type. So, this algorithm can be applied to both functional unit minimization as well as register minimization. With an understanding of the left edge algorithm, we come to the end of module 1 of lecture 7.